Hello. I'm going to explain some follow-up I did on my graduate capstone project. For the original graduate capstone project, I was looking at a way to predict phosphorus levels in the Snake River here in southern Idaho. The reason that's a problem is because if you have too much phosphorus in the waterways, it can essentially kill the fish. I left a lot of the same explanations I did in the first code, but the main difference between here and what actually went into my project is my machine learning method. You can see in the title right here, I did the linear regression, since that was one of my recommendations I made to optimize this project. Again, I'm loading a bunch of packages I need. I was fast and loose on the edits with this, so there's some things I don't need, such as logistic regression. But that said, my data cleaning, everything else is going to be the same as my original project. So I want to get to the part where I show the results from linear regression. So this is my linear regression before transformation. There are 4 actual fields or variables that can actually be used as predictors themselves on the phosphorus target. But for this model right here, I'm just including all of my quantitative variables. Again, I start with normalization, did it mathematically. Subtract the mean from every record and then divide that by the standard deviation. I use the stats model API because it gives you all your coefficients cleanly when you print a model summary, as well as R squared, adjusted R squared, so it's easier to see accuracy metrics and predictability metrics, such as AIC and BIC. You want those to be lower if possible. It also gives you an F statistic. You may recognize the F statistic as something that's linked with ANOVA, which makes sense here because there's multiple variables. So this is a statistically significant model. If you have an alpha of 0.05, I've been assuming that on my projects. But here you can actually see the p-values for each of your coefficients. So here, calcium, not statistically significant, way high p-value. Sulfur, same thing. And then pH as well. I'm sure I'm missing something. Here we go, manganese, 0.5, not 0.05. So taking this initial model, I look at the cross-validation, and it's not great. I'm getting a score of not even 10%. Using holdout testing accuracy, a train test split of 70% training data, 30% testing data, I can see that on this particular data set, I'm getting a accuracy score of about 75%. So this model works well on this particular data set, on this particular split. Again, I'm just showing my coefficients and how they affect phosphorus. You'll notice I have a very low constant, almost 0, and then very, very low absolute values for my coefficients, except for total solid. That's has a positive correlation with phosphorus levels, and it's an order of magnitude higher than all of the rest. This makes sense because if dirt washes into the river, there's more likely to be phosphorus in that sediment or soil. Here's the intercept on that model, which is 0.127. Previously, if you look at the original Capstone project on logistic regression, these are the only 4 predictors that can actually be used to predict phosphorus levels. Because by the time you're measuring phosphorus, you're also measuring all of the other chemicals in this data set. Doing a train test split, keep that the same, but I change my training data here. I again look at the linear model, so the statistical significance of the entire model. Here you can see I have my constant, my coefficients, again total solid very high, and everything else kind of negligible. It's R squared, it's about similar. It was 0.81 last time, now it's 0.83. And p-values, pH still not statistically significant, EC neither as well. So these two, flow rate, meters cubed per second, and total solid, those are going to be the statistically significant predictors in this model. But when I run cross-validation accuracy scores, I'm still getting 10%, so what, 1% improvement with this? And my holdout testing accuracy is actually lower. Now it's about 66%. Again, I just look at my coefficients printed out here. You can see them in the model as well, but just being thorough. And same phenomenon I'm seeing with total solids. Order of magnitude higher. 2 orders of magnitude higher than all of the rest. Again, I export my clean CSVs, and then I ran a linear regression on my quantitative variables and total phosphorus measurements. This is basically calculating R and R squared. Individually, how do each of these fields independently correlate to the total phosphorus levels? Again, I have low, less than 2% on a lot of these. That's very low, 10 to the negative 5. Till you get to total solids, which has a 41% predictability effect on my total phosphorus levels. And total nitrogen as well has got a high R squared here, 0.31. I ran the model again with only the statistically significant variables from the first model. So that includes all my chemicals. I remember calcium, manganese, etc. Others, they had high p-values. Once kicking those out and running the constant again, you see my R squared on the entire model, linear model, does go up to 0.88, so that's good for predictability. For my holdout testing accuracy, I'm getting 75%. That seemed to be pretty consistent, and that was one of my goals, to stay above 70%. The cross-validation accuracy score suggests that for this particular model, it's going to have poor general use for predicting phosphorus levels. Let's see. This was a prediction level that I used from the stats model that I generated before, as opposed to cross-validation, and now I've got about 1% accuracy. Linear regression, though I thought it would help me, it did increase my predictability and my R squared in the overall model, but it actually resulted in lower accuracies, so didn't do great. And here's my summary here. You can see the R squareds. They do increase as you stick to statistical significance, but the lean model and this have similar predictability, R squared. Holdout testing accuracy is decent, 60% or higher, but that probably suggests that this model overfits to this particular data set. If I were to try to predict phosphorus in, say, another river system with the same chemical ions, pH, flow rates, etc., this model would probably not be great in general use. That said, I was limited by the record count, and I will keep working on this at work and see how I can improve it. Thanks for your time.